China just finished building its own machine to print computer chips. And this thing is not small. Reports say it takes up an entire factory floor. That sounds strange when you hear the next part. The machine it is trying to match, built by a company called ASML, is only about the size of a school bus. So why does China's version need to be 20 times bigger just to do the same job? That one question was what pulled me into this story. At first I thought this was going to be a simple copy job. China sees a machine, China copies the machine, done. But the more I looked into it, the more I realized that is not what happened at all. China could not just copy this machine because almost none of the important parts were something they were allowed to buy or even look at closely. So instead, engineers in China had to solve the same problems ASML solved, but using their own ideas, their own materials, and their own tricks. Some people have started calling this China's version of the Manhattan Project. That might sound like an exaggeration, but once you understand what this machine actually does, it starts to make a lot of sense. This is not just a big printer. It is one of the hardest machines humans have ever built. A single one of these machines can cost more than $150 million. It has tens of thousands of parts. Some of those parts have to be more precise than anything else ever made by human hands. And for almost 20 years, only one company on Earth could build a working version. That company was ASML, based in the Netherlands. Without this machine, you cannot make the tiny, fast, powerful chips that go inside phones, laptops, cars, and even weapons. Without it, a country is stuck making older, slower chips forever. That is exactly the situation China has been in. For years, other countries, especially the United States, have been blocking China from buying this machine or the parts needed to build one. The idea was simple. If China cannot buy or build this machine, China cannot make the best chips. And if China cannot make the best chips, it falls behind in almost every kind of modern technology, from smartphones to fighter jets. Think about how much of daily life now runs on tiny chips. Your phone, your car, your smartwatch, the servers that power the internet, and every new artificial intelligence tool you have heard about, all of it depends on chips getting smaller, faster, and more efficient every single year. Whoever controls the machines that make these chips does not just control a piece of technology. They control a huge piece of the future economy and a huge piece of future military power too. That is why so many countries are treating this single machine like a national treasure worth protecting at all costs. That is also part of why the Manhattan Project comparison keeps coming up. The original Manhattan Project pulled together some of the smartest scientists in the country, along with a massive pile of government money, all aimed at solving one incredibly hard problem as fast as possible. China's EUV push looks similar in shape. Dozens of universities, research labs, and state-owned companies have reportedly been pulled into this single effort, all pointed at the same target. Billions of dollars have gone into it. Thousands of engineers have been assigned to it. And unlike a normal business project, failure here is not just about losing money. For China, falling behind on this technology means staying stuck behind a wall that other countries get to build past. So China decided to build its own. And what they ended up with is strange, oversized, and in some ways completely different from the original. In this video, we are going to break this machine apart piece by piece. We will look at the part that makes the light, the part that aims the light, the part that keeps everything cool, and the people who had to learn how to put it all together. Along the way, you will see exactly why this machine had to be so huge, why one gas from a party balloon almost became China's biggest problem, and why the hardest part of this whole project might not be a machine at all. Before we get into that, if you are the kind of person who wants to actually understand how the technology behind your phone and your laptop is made, instead of just hearing scary headlines about it, this channel is for you. I break these stories down piece by piece with no confusing jargon. So if that sounds like something you want more of, go ahead and hit subscribe now, because the next video in this series digs even deeper into how these chips reach your pocket. Now, to understand why this machine is such a big deal, we need to start with the one thing every single one of these machines depends on. Something so strange that for most of history, nobody even knew how to make it on purpose. Section 1, the light that should not exist. Think about how a chip actually gets made. You start with a flat piece of silicon, and you need to draw incredibly tiny lines and shapes onto it. These lines are so small that thousands of them could fit across the width of a human hair. To draw lines that small, you cannot use a pen. You cannot even use a normal beam of light, like the light from a flashlight or a laser pointer. You need something much, much smaller. Here is a simple way to think about it. Imagine trying to paint a very detailed picture using a giant paint roller. No matter how careful you are, the lines will be thick and blurry. Now imagine switching to the tiniest paintbrush ever made. Suddenly you can draw fine, sharp details. Light works the same way. Light travels in waves, and the size of those waves decides how fine of a line you can draw with it. Big waves make blurry lines. Tiny waves make sharp, thin lines. To make today's fastest chips, engineers need light with an incredibly tiny wave size, so tiny that scientists gave it a special name: extreme ultraviolet light, or EUV for short. This light is so short and so extreme that it does not really exist anywhere in nature in a usable form. You cannot flip a switch and turn it on like a light bulb. You have to create it from scratch, every single second, over and over again, with almost no room for mistakes. This matters more than it might sound like at first. The chips made with this kind of light are the ones that end up inside the newest phones, the fastest laptops, and the powerful computers running today's artificial intelligence. Without access to this light, a country can still make chips, just not the best ones. It is a little like being allowed to build cars, but only ever with engines from 20 years ago. You can still drive, but you will never win the race. So how do you make light like that? ASML's answer is honestly one of the wildest pieces of engineering you will ever hear about. Inside the machine, a system fires 50,000 tiny droplets of melted metal called tin every single second into an empty chamber. As each droplet flies through the air, a small laser flattens it into a thin little disc, kind of like squashing a ball of dough with a rolling pin. Then, a split second later, a second, and much more powerful laser strikes that same flattened droplet. The hit is so intense that the tin does not just melt or burn. It turns into something called plasma, which is basically matter that has been blasted apart into a super hot, glowing cloud. This cloud reaches temperatures close to 200,000 degrees. That is many times hotter than the surface of the sun. As that scorching cloud cools down for a tiny fraction of a second, it gives off a burst of the exact light needed, the extreme ultraviolet light. Now remember, this whole process has to repeat 50,000 times every single second, hitting a target that is flying through the air smaller than a speck of dust. And it has to work perfectly almost every time. To put that speed in perspective, in the time it takes you to blink your eyes once, the machine has already fired at and hit hundreds of these flying droplets back to back without missing. It is a bit like trying to shoot a bullet out of the sky using a second bullet, except you have to do it successfully 50,000 times in a row, every single second, all day long, without a single miss slowing down the whole factory. If that sounds insane to you, you are not wrong. It took ASML decades of failed attempts, wasted money, and stubborn engineers to make this idea actually work in a factory. Once they finally cracked it, this became the standard method every EUV machine on Earth was built around for almost 20 years. That is the machine China suddenly needed to recreate, without being able to buy the key parts or copy the exact blueprints. So Chinese engineers had a choice to make. They could try to rebuild ASML's tin droplet method from scratch, which is incredibly hard, without decades of ASML's specific know-how. Or they could search for a completely different way to make the same kind of light. Based on public reports, it looks like China is actually trying both paths at once. The second path is the interesting one because it is not new. It is an old idea that ASML itself tried and gave up on years ago. It is called laser-induced discharge plasma, but do not worry about that name. Think of it this way instead. Instead of firing 50,000 flying droplets every second, this method uses two metal discs that spin slowly, kind of like two small wheels facing each other. Each disc dips into a pool of melted tin as it spins, picking up a thin coating on its surface, the same way a car tire picks up water on a wet road. These discs are also hooked up to giant batteries full of stored electricity. A small laser fires at one of the discs, just enough to knock loose a little puff of tin vapor that floats in the gap between the two discs. Then, all that stored electricity gets released at once, sending a massive jolt of electric current straight through that little cloud of vapor. That jolt squeezes the cloud incredibly hard, turning it into the same kind of blisteringly hot plasma we talked about before, hot enough to give off the same extreme ultraviolet light. The exciting part is that this method sounds much simpler. There is no need to fire lasers at 50,000 tiny flying targets every second. You are not chasing a moving target at all. The discs just spin steadily and sparks jump between them again and again. On paper, that should mean fewer mistakes, simpler machinery, and lower costs. So here is the obvious question. If this method is simpler, why did not ASML just build their machines this way in the first place? The answer is that they tried. About 20 years ago, ASML actually experimented with this exact idea, but they ran into a wall they could not get past. The problem was never making the light. The real problem was making enough of it. A real chip factory does not need just a tiny flicker of this special light. It needs hundreds of watts of it, flowing steadily, hour after hour, day after day. Without enough light, every single wafer takes far too long to finish, and no factory on Earth can afford to sit around waiting. Here's a simple way to picture the problem. Imagine trying to cook a full dinner using only the heat coming off a small light bulb. Eventually, in theory, with enough patience, you might get there. But no restaurant could ever survive running its kitchen that way. That is exactly what happened with this spinning disk method years ago. As engineers pushed more and more electrical power into the little cloud of plasma, the cloud simply grew bigger, not brighter. And the mirrors used to collect the light could only grab a small portion of a bigger, more spread out cloud. So engineers kept pouring in more power without actually getting more usable light out the other side. Eventually, this method topped out at around 30 watts of usable light. Compare that to the newest version of ASML's tin droplet method, which some prototypes have reportedly pushed past 700 watts. Once ASML saw that gap, they simply moved on and never looked back. Not because the idea was impossible, but because back then, it could not be scaled up to run inside a real working factory. This brings us to the most important part of the whole story. China is not betting that this older, simpler method was secretly better than what ASML chose. China is betting on something else entirely. They are betting that today's technology, in 2026, is simply better than the technology that existed 20 years ago when ASML first gave up on this idea. Better electronics, better materials, and decades of extra research might be enough to finally push past the wall that stopped engineers back then. It helps to understand why watts matter so much here. Think of watts as a measure of how bright and steady this special light actually is. A dim, weak light means each wafer has to sit under the beam for a longer stretch of time before enough of a pattern gets printed onto it. A bright, steady light means the wafer finishes much faster, and the whole factory can push out far more finished chips every single day. So the gap between 30 watts and 700 watts is not just a number on a page. It is the difference between a machine that could realistically run a busy factory around the clock and a machine that can only manage a slow trickle of finished chips at a pace no real business could survive on for long. So far, reports suggest China has built working versions of both methods, the original tin droplet approach and this alternative spinning disk approach. Both are still producing far less usable light than what a real factory would need to run at full speed. But for the very first time, China has an EUV light source of its own, built without needing permission from anyone else. At this point, it might feel like the hardest problem is already solved. Once you have the right kind of light, you are done, right? Not even close. Because now comes a challenge that is honestly even harder than creating the light in the first place. You have to figure out how to aim that light perfectly onto a silicon wafer without losing almost all of it along the way. Section 2. The mirror. Nobody else could build. Think about how you normally focus or bend light. Glasses use curved glass to bend light so you can see clearly. Cameras use glass lenses to focus an image. Even a simple magnifying glass uses curved glass to bend sunlight into a tiny, powerful point. Glass is amazing at bending and focusing light. Except when it comes to this specific kind of light, glass is completely useless. At this extremely tiny wave size, almost every material on Earth, including glass, does not bend the light at all. It simply swallows it up and absorbs it, like a sponge soaking up water. So engineers had a serious problem. How do you aim and focus light that gets eaten by every lens you try to use? Their answer was to throw lenses out completely and switch to mirrors instead. Rather than bending the light through glass, the machine bounces the light off a careful chain of mirrors, sending it ricocheting step by step, almost like a trick shot in a game of pool, until it finally lands precisely on the silicon wafer. But do not picture a normal bathroom mirror here. These are some of the most demanding objects human beings have ever manufactured. Each mirror is built from dozens of layers stacked on top of each other, each layer thinner than a soap bubble, made from materials called molybdenum and silicon. Every single time the light bounces off one of these mirrors, it loses at least 30% of its strength. And remember, the light already has to bounce off several mirrors just to reach the wafer. By the time it finally arrives, only a small fraction of the original light is left. That means there's almost no room for waste or error anywhere along the way. Every mirror has to be built with a level of smoothness that is honestly hard to even imagine. Here is a way to picture just how smooth these mirrors need to be. Imagine you shrank the entire country down so it was as smooth and flat as one of these mirrors has to be. Under that rule, the tallest mountain in the whole country would only be allowed to stick up a few inches. That is the kind of insane precision we're talking about, spread across a curved surface roughly the size of a dinner plate. Building a mirror. This precise is already unbelievably difficult. But here's the twist. Measuring whether you actually succeeded is almost just as hard. You need special tools just to check whether the mirror is smooth enough, and those tools are nearly as rare and specialized as the mirrors themselves. For decades, there was really only one company on the entire planet that had mastered this art. The company is called Zeiss, based in Germany. It is not that Zeiss discovered one magic secret formula. It is that they spent over 30 years slowly perfecting every single tiny step involved, from polishing the surface to coating it with those paper-thin layers. to measuring it with extreme precision, to lining it up perfectly inside the machine. That 30 years of trial and error is the real gap between building an ordinary mirror and building a mirror that can survive inside an EUV machine. Here's what makes it even trickier. A single speck of dust landing on one of these mirrors during production could ruin months of work. So these mirrors are not built out in the open like a normal factory item. They are built and handled inside special rooms that are cleaner than a hospital operating room, where workers wear full suits from head to toe, and even the tiniest bit of dust in the air is filtered out constantly. Every step of polishing has to be checked and rechecked, sometimes for months at a time, before a single mirror is considered finished and ready to use. So here is where things get genuinely interesting. How exactly did China manage to recreate 3 decades of hard-won mirror-making knowledge, all without any help from Zeiss? And why does China's version of this machine reportedly take up an entire factory floor, while ASML's fits neatly into something the size of a school bus? The answers to both of those questions turned out to be more clever than I originally expected. China broke this enormous challenge down into smaller, more manageable pieces. One of the most important pieces landed on the shoulders of a research group called the Changchun Institute of Optics. This group had already spent years building extremely precise optical equipment for things like space telescopes, so they were not starting completely from zero. But building a mirror for a space telescope and building a mirror for an EUV machine turned out to be 2 very different challenges. For an EUV mirror, the surface has to be smoothed down to about 50 trillionths of a meter, a level of smoothness smaller than the width of a single atom. That specific kind of polishing skill, especially on a curved surface, really was Zeiss's closely guarded secret sauce, built up slowly over more than 30 years of practice. And the difficulty does not stop once the mirror is built and installed. Inside a working EUV machine, these mirrors are constantly getting hit by leftover bits of hot tin debris and intense radiation from the light source itself. Keeping these delicate coatings stable and working properly for years inside a machine running non-stop in a real factory is an entirely separate challenge on its own. Public reports suggest Chinese research institutes have already managed to build working domestic EUV mirrors and successfully installed them into prototype optical systems. That is a genuinely impressive milestone. But matching the actual quality of Zeiss's mirrors is a completely different story, especially when it comes to how much light they can reflect and how long they can hold up under heavy use over the years. So China seems to have made a clever engineering trade-off here. If your mirrors cannot reflect quite as much light and your light source is not quite as bright, one way to make up for that gap is with raw size. Build bigger light collectors, use more powerful lasers, stretch out the path the light travels, add extra mirrors along the way. It is basically the engineering version of a simple idea we all understand. If you cannot make something perfectly precise, you can sometimes just make it bigger instead and let the extra size make up the difference. That trade-off may be exactly why China's prototype reportedly needs an entire factory floor to operate, while ASML's finished machine fits into something roughly the size of a school bus. Reports suggest the Changchun Institute of Optics has now successfully connected its homemade optical systems into China's prototype scanner. To be clear, that does not mean China has matched Zeiss's quality. Far from it. The overall performance of the optical system still appears to be well below what commercial EUV scanners can do. Still, this counts as a real and meaningful milestone. For the very first time, China appears to have assembled a fully domestic optical system that is actually capable of operating inside a working EUV scanner, built without needing help or parts from Zeiss. And that brings us to the next problem hiding inside this machine. It is not something you can polish, smoother, or engineer your way around. In fact, it is one of the lightest and simplest elements found anywhere in the entire universe. Section 3, the party balloon. Gas that could break everything. Here is a twist you probably did not see coming. One of the biggest threats to this entire multi-billion-dollar machine is the exact same gas used to fill balloons at a birthday party. That gas is helium. It might sound almost funny at first, but helium turns out to be absolutely essential, not just for running the EUV machine itself, but for the entire process of making computer chips in general. And the reason is simple. There's nothing else on Earth that can do everything helium does all at the same time. Helium is used to carry heat away from some of the hottest, most delicate parts of the chip-making process, cooling things down without damaging anything. It does not react chemically with the extremely sensitive optics or with the silicon wafers, which matters a lot when you are working with parts this fragile and expensive. And because helium atoms are so incredibly tiny, engineers also use helium to detect leaks that are far too small for any other gas to reveal. If you take helium away, chip production simply grinds to a halt along with it. And these machines do not sip helium a little bit at a time. They drink it by the truckload. A single advanced chip factory can require somewhere between 5,000 and 20,000 cubic meters of helium every single month. To put that into perspective, that would be like filling millions and millions of party balloons every single month just to keep one factory running smoothly. Helium shortages are not some brand new problem either. Hospitals around the world have run into the exact same squeeze, because the machines used for MRI scans also depend heavily on helium to stay cold enough to work. When helium supplies get tight, hospitals sometimes have to delay scans, and party balloon companies quietly run out of stock too. Now imagine that same fragile, limited supply also being fought over by every major chip factory on the planet, all trying to build the most advanced technology of the decade. That is the squeeze China is stepping into. Here is where the real problem starts for China. Unlike most of the raw materials used in chip making, helium is genuinely hard to come by. China imports roughly 85% of all the helium it uses. Domestic production inside the country sits at under 900 tons a year, while imports have reportedly climbed past 4,900 tons. Historically, most of that imported supply came from just two countries, Qatar and Russia, and in recent years, both of those supply routes have come under serious pressure and disruption. To make things even trickier, helium is nothing like oil. You cannot just pump it out of the ground and store it safely in a tank forever. Helium is shipped around the world as an extremely cold liquid, and it is very sensitive to time. If a shipment gets delayed for too long, the helium slowly boils away and escapes, drifting off into the atmosphere. Once that happens, it is simply gone for good with no way to get it back. Meanwhile, the largest known reserves of helium in the entire world sit mostly in the United States and in Qatar, two places China cannot always count on for a smooth, uninterrupted supply. So now you have a country trying to build an entire homegrown EUV chip-making system. While depending heavily on a critical material, it does not fully control itself. And here is the part that makes this such a big deal. This is not only China's problem, this is genuinely everyone's problem. It affects TSMC in Taiwan, Samsung in South Korea, Intel in the United States, and SK Hynix as well. Essentially, every advanced chipmaker on the planet is pulling helium from that exact same fragile global supply chain. According to reports, China's government has responded by putting an emergency ban on almost all helium exports leaving the country, essentially hoarding every bit of helium it can get its hands on to keep domestic chip factories running. The deeper you dig into this whole story, the clearer one thing becomes. This EUV machine is not being held back by just one single missing invention. It is being held back by thousands of tiny, mostly invisible dependencies, all stacked on top of each other. Some of those dependencies are ridiculously expensive mirrors. Some are decades of quiet, patient optical know-how, and some, somehow, turn out to be as simple and ordinary as a colorless gas that most people never think about at all. Even if you manage to solve the light, build workable mirrors, and lock down a steady supply of helium, one final challenge still remains, and it might honestly be the hardest one of all. Section 4. The one thing. No sanction can ever stop. You can have the light source figured out. You can have working mirrors installed. You can even have a reliable supply of helium locked in. But none of that matters if you do not have people who actually know how to make every single one of those pieces work together, smoothly, reliably, for years on end, inside a real factory. And here is the one truth that no export ban, no sanction, and no trade restriction has ever been able to fully stop. You can absolutely block shipments of machines and specialized parts from leaving one country and entering another, but you simply cannot block knowledge that is already sitting inside someone's head. That fact alone may end up being one of the most important advantages China has had this entire time. So while China was busy pouring money into laboratories, research institutes, and factories, it was also quietly investing in something else just as valuable: human experience. Some of the most talented engineers working overseas, including people who had spent years working directly on EUV technology at companies like ASML, were recruited to return home to China and take part in some of the country's highest priority technology programs. One well-known example that has been reported publicly is an engineer named Lin Nan. He reportedly spent years at ASML working specifically on the EUV light source, widely considered the single hardest and most important part of the entire machine to get right. After returning to China, he joined the Shanghai Institute of Optics and Fine Mechanics, where his team quickly began publishing new research and filing patents connected to generating EUV light. Stories like this are not one-time events either. Across the world, there has been a quiet but very real competition to attract engineers who have worked on advanced chip technology, with countries and companies offering higher pay, better labs, and bigger research budgets to pull skilled people toward their own programs. A single engineer who spent 10 years solving one narrow, extremely specific problem at a place like ASML carries knowledge in their head that would normally take a brand new team years of trial and error to rediscover on their own. Bringing even a handful of these experienced engineers home can save a national program years of wasted effort. And China is clearly pouring enormous amounts of money and talent into this effort, because you can actually see the results showing up in the data. If you look at the number of research papers published on EUV lithography over the years, a very clear pattern jumps out immediately. For a long stretch of time, China published relatively few papers on this topic compared to other countries. Then, starting sometime around 2020, that number suddenly exploded upward. Dozens of separate research teams began attacking different pieces of the puzzle all at the same time, working in parallel rather than one after another. So after everything we have covered, where does that actually leave things right now? According to current reports, China now has a working EUV prototype that is producing somewhere around 100 watts of usable light. Compare that to ASML's regular production machines, which typically deliver around 300 watts, with some of ASML's very newest prototypes reportedly reaching as high as 700 watts. That is still a very real and very significant gap. But here's an important question worth asking honestly. Does China actually need to match ASML watt for watt in order for this whole project to count as a win? I do not think it does, and here is why. Right now, China's leading chip maker, a company called SMIC, is already producing its most advanced chips using an older method known as quadruple patterning. In simple terms, this means passing the exact same silicon wafer through an older, less advanced machine 4 separate times in a row, layering patterns on top of each other over and over until they get close enough to the fine detail that a true EUV machine could achieve in a single pass. This method does technically work, but it comes with serious costs. Fewer than half of the chips made this way actually turn out usable. It takes far longer to finish each batch, and the whole process gets dramatically more expensive. Eventually, the basic laws of physics simply stop you from shrinking things any further using this method, no matter how many extra passes you add. This is exactly why a working, even imperfect domestic EUV machine does not need to become the single best machine in the entire world in order to matter. It only needs to be a real improvement over the messy, expensive workaround China is currently relying on. Even if it produces fewer finished chips per hour, even if it cannot yet compete commercially with ASML's machines, even if the percentage of usable chips it produces is still far below ASML's numbers. As long as it can genuinely replace that clunky 4-pass method, it already counts as a massive win for China's entire chip-making industry. It is also worth remembering that ASML itself did not build a perfect, ready-to-use factory machine overnight either. It reportedly took ASML somewhere around 12 full years to go from their very first working EUV prototype all the way to a finished, reliable commercial product that factories could actually depend on every single day. China will almost certainly need a good chunk of time to make that same journey too. But there is one major difference worth pointing out here. For ASML, this was primarily a business project, driven mainly by profit and competition in the marketplace. For China, this is something much bigger than a simple business decision. It is a strategic move. The real goal here was never really about building the single best EUV machine on planet Earth. The real goal is building a machine that China fully controls on its own without needing permission, parts, or approval from any other country ever again. And even once a working prototype like this exists in a lab, there is still one more massive step left to take, arguably the hardest step of the entire process. You have to somehow turn a machine that works successfully one single time into a machine that can run reliably 24 hours a day, printing hundreds of finished wafers every single hour for years and years without breaking down. That gap between something that worked once in a controlled lab setting and something that can survive the brutal daily grind of an actual factory floor is enormous, and it is where so many promising projects around the world have quietly stumbled and failed before. So that is the real story behind China's giant factory-sized chip printing machine, and every single hidden problem it had to solve just to exist at all. If you learned something new today, do me a favor and hit that like button, subscribe if you have not already, and tap the notification bell so you never miss the next deep dive like this one. Now I want to hear from you. Do you think China will actually manage to close this gap with ASML within the next 10 years? Or is this a lead that is simply too big to catch up to? Drop your honest take in the comments below. I read every single one. And if you enjoyed this video, go check out our other breakdown on how chip factories actually work behind closed doors, or our video on the newest breakthroughs in chip design. I think you will enjoy both of them. Thanks for watching, and I will see you in the next one.